Hi, everyone, and welcome to this third Matlab tutorial. And of course, since this is the last major assignment before the final project, you should all say, yay. Okay, great. Um, so in this one, we're going to continue our analysis of beams. And that's why I got this really cool picture up here. I thought it was kind of cool. But we're going to use different sizes, different materials. And so just figured I can hopefully get you interested in on that. So here are the objectives. We're going to combine our analysis of beams, nice engineering thing, uh, with that previous lab, and then combine that with the capabilities of MATLAB to look at a lot of scenarios, not just the one that we saw before. And now, one of the things you might be um, wondering is whether, hey, I've learned how to use Excel. Awesome. Excel is one of my favorite tools. Spreadsheets in general are a great, great tool. But there may very well come a time in the not too distant future where you're going to need something more powerful. More powerful than Excel. I just learned to get rid of my TI-80 stupid calculator. Well, uh, this is well beyond that. Um, so we're going to learn to that, and I'll show you that this can be used. Now, Excel is a lot easier to use, okay? But this, um, once you learn it, once you hit that learning curve, you're gonna say, "Oh, now I know what to use this for." And so, if you thought ever run into the whole, ever run into something in Excel and say, "Boy, I wish it could do this." MATLAB probably can. Um, so here we go. Here we go. We're going to um, then this is going to be better than other calculation techniques because we can do a lot more with it. We're going to use something called structures and it's similar to classes in some of the other programming languages if you've ever used them, but you'll see that shortly. So let me see if I've got. Okay. Um, that was in the way there. So, so if you haven't done the first two labs, you're in trouble. So don't even go with this lab until you've done the first two. So if you want to look at the beam analysis and see how it works, um, go there. Also, that's where the links are that you might want to see for looking up stuff. So I've got links there if I've got the beam reaction table, I've got elastic moduli and properties of structural steel. So um, so these are all great references for you to use. And back to the assignment. So we're going to use structures instead, and we're going to use three sets of parameters with a load and a beam length. So, 10,000 pounds or 100,000 pounds, whatever it is, and a certain length. So whatever length that is and the load, that's going to be three. You're going to use three sets. So setting up one is kind of annoying. You got to learn how to make sure all those things, but then you just copy and paste and change the numbers. So whether it's 3 or 10 shouldn't matter, but at least not that much. So we're going to do three just to give you an idea of how that works. Three different beam cross sections. So basically beam sizes, bigger and smaller. Uh, and then three different materials. Well, steel is a material, but it's a general type of material. There are multiple types of steel, like hundreds or thousands of different steels. In fact, there's a possibility of infinite combinations for steel. Um, so just throwing that one out there for it. But you're just going to use three different ones. I'm going to use some really interesting numbers, and um, hopefully, I know you're going to find your very own to use. Okay, so we're going to begin a new MATLAB script. Already done here. I got untitled number 3. Of course, I'm going to call it something else. So we're going to save it. Make sure you save it. So we're going to save as, and we're going to call it beam analysis 3, North Carolina. Great. All right, so I've got my name, but I can do this. You can't. You have to put your name in the file name, and that file name can't have any spaces in it. Okay, that's how it works because it's old school, I guess. But your names, and you can do this in pairs or by yourself. Your names have to be in the file name, and then you're good to go. We also are going to put that at the very top. So Matlab assignment 3 multiparameter. Oh, I can spell that. Great. Beam analysis. I really have to learn how to type better. Okay, and then you're going to put in your names up at the top here too. All right. So that's the double comment thing. That's a header kind of thing. And so then we're going to put, initialize everything. So initialize all spaces, and gonna clear all, close all, and CLC. So that's the way you should start out these programs. Maybe this is bad. I don't know. I'll talk to a better programmer than myself. But I find that, start with a clean slate with everything. So now we're going to start a new section. And the first thing we're going to do, let me see if I can draw this or something like that, just to give you an idea of where we're going to go with this. So first thing I'm going to want to do is I'm going to want to set up my parameters, especially anything global. Okay. So, and I'm going to set up my parameters in structures. Okay. So I'm going to do that first. And then once that's taken care of and I get everything, I like doing it this way myself because I can see them boom, 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 one right after another, and it makes I keep my notation consistent and so on. It's hard when you're trying to do things up here and down here that are related and should be like parallel. So I like doing that first. I think it's a good way of doing it. And then we are going to make calculation loops, okay? And we're going to create new structures using these calculation loops. So we're going to have, within that calculation loop, we're going to have a loading type. So that's going to be, whether it's simply supported or whatever, we're going to have loading setup. So that's, length and load and there's that. And then we're going to have materials. Okay. Oh, and also cross sections. I think I should have put that in there. So cross sections. Okay. So we're going to have like 4 loops running, and it's going to immediately calculate anything in there. And then I think what I have set up, the way I actually have it set up, is loading type itself is not going to be a loop. I'm going to have 2 separate nested 3 loops, loading type 1 and loading type 2. And then 3 is going to be output. Or not so much 3, but the next thing is going to be output here. Okay, so that's basically the structure of what I'm trying to go along. So watch for that organization and strategy. All right, so clear all that out. So this shouldn't take too terribly long. The worst thing about this is understanding what I'm doing, not what I'm typing. I hope that makes any sense to you, because these structures are not as easy as like the first assignment was like, duh, multiplication, division, natural logs, that kind of stuff. That was pretty easy. This isn't. This is a data type structure. So I'll try to slow down where it makes sense to slow down. All right, so we are first going to set up variables. Okay, and I'm going to delete variables and I'm going to call it basic data structures. All right, now I'm going to stop commenting here, and you're going to start commenting a lot more. Every step of the way, you should be commenting. I'm going to show you how these things work, but you have to tell me that you know what you're doing. All right. So I'm going to set up loading parameters. So I'm going to call this one loading 1, and I'm going to call this one loading 2. Okay. And I'm going to do 2 loading situations, whereas you're supposed to do 3. All right, but it's not too bad. So I'm going to create a structure. The structure has a bunch of related variables. They can be text, they can be data, numbers, whatever. We're going to have a combination of text and numbers here. So it is this struct is actually a command to create a structure named loading 1 that has these things: length underscore foot 10. Okay. And you see, you can see that, it comes up with a field and a value, Of course, I can't type properly, so there's that. But here's my field: length feet, comma 10. So we're making a field called length feet, and it's 10. But then we're making another one. We're going to call it load pounds, and it's going to be 10,000. Okay. I'm just going to copy that because I'm lazy. And I'm going to make a new structure called loading 2, and its first field is length feet, and we're going to call that 2. And load pounds is going to be 20,000 there. Okay. So, by the way, you are expected to use your own data, whether, don't use mine. By the way, I have specifically set mine up to be wonky and weird. So you're gonna have to look up your own stuff to make it a little bit more reasonable. So just because I mean like that, because I want you to actually do stuff so that you can learn things. Okay, so I'm gonna put the semicolons at the end, and then now I'm going to make some more structures. So that's my loading structure. Boom. So we can go over here and check this one off. Well, I did 2. You're supposed to do 3. All right. So we're going to do some new ones. I'm going to call it shape 1. You should do it with your own variables because mine are lame. Okay. And I'm going to use that struct thing again. And this is going to be a little bit more in depth, but it's the same thing: field value, field value, field value. So these shapes, as you saw before, where'd that shape stuff go? Is this it? There we go. Okay, so this shape, this 30 by 211, has a variety of data associated with it. So it's got a designation, weight per foot, area, and so on in these various units. So for each shape that I want to use, I'm going to input this data. Now, imagine, if you will, that you're a lot smarter than we are, and you can type this stuff in and import the data over here automatically into structures in Matlab. Okay, if you can program that, awesome, you'll get an A for this assignment. But until that time, we're going to have to enter these things in by hand. But you can see that if we were able to do that, we could very quickly finish this assignment, hit the button, and do a whole bunch of analysis real fast. That'd be awesome. But we're going to do this by hand. So I'm going to make a structure here called called shape 1, and I'm going to put in it name, or maybe I should just call it designation, because that's what they have over here. All right. Designation or desig. And we're going to do, let's go back to here, right? And we're going to do W29 by 200. By the way, these are really large beams. You might want to use something smaller. I don't know. All right. So next one up is, I guess I can go back to here. I'm going to use linear weight pounds per foot. And we're going to call it 200. And then area inch squared is going to be 62.2 and so on. Oh, wait, is that what I wanted? No, that's the other one. That's 60. So I'm going to go through each one of these fields and enter it in. So it's going to be pretty boring. Now might be the time that you hit the 2x button. Okay. So area inch squared. Okay. Okay, so I cheated there. That's awesome. All right, so what did I do? Give you a little more space here to see. All right, so I created the structure. It has each one of these different things. So this is the flange width. That's how wide the whole thing is pretty much. The flange thickness. So that's how thick that top part of the flange is. Where'd that go? Okay, so the flange is this top part here. So the thickness would be from here all the way to here. The thickness of the flange is this right here. Hard to show you here, but yeah, this right here is the thickness of the flange. Okay, this is the web over here. So this is the thickness of the web, sometimes referred to TW, something like that. So that's the thickness of the web. The depth of the whole thing is from top all the way down to the bottom. So yeah, that whole distance. Area, of course, is the rest of it. So hopefully that should be good enough to work with. So you understand what we're entering in. Oh, probably should clear that out. Okay, so those are the various elements. And some of this we went over the other day or last week. So I'm going to copy this, going to enter this in. So shape 2. And I'm going to do the W27 by 130. Linear weight. Make sure you enter these in accurately, otherwise you'll be in trouble after that. So each of these fields is going to still come up, and as long as they're identical, that's going to work out really nicely. So and finally, our Rx is going to be 11.2. All right, so again, watching me type is like watching grass grow, but we're getting there fast. Okay, so next I'm going to create material. So we're going to do the same kind of thing. Going to make another structure. So each of these structures is combines a bunch of data that's closely associated with itself. So this is for a material. Materials have a lot of different properties called material properties. So I'm going to go with that. Material 1 equals struct. And now I'm doing this with these colons, these parentheses and these numbers here because it's going to do a count for me using it. So I'm doing that for a very specific reason. So you should do the same kind of thing. Don't necessarily call it loading, but do 1, 2, and so on, because that's going to help you finish this nicely without killing yourself. Okay, so struct. The first thing we're going to do is call it a give it a name, or it could be a designation as well, but we'll stick with that for the shapes. And call it steel A30. And make sure you have all of these fields here, because I use them all. Yield strength, PSI. Notice how I have it labeled, again, with the units. That's always very helpful. And then elastic. No, I want to point out something to you in a second. Modulus underscore PSI. Okay, so what I want to mention to you here is that we use the some of these things, these fields have values after them. You don't need the quotations for the numerical values like this, but you do need it for this. So now the designation of shape number 1 is W29 by 200. So that's the designation for that. But then everything else is numbers. So here we have another name, a designation, if you will, steel A30, and it has to be in the single quotes. But for the yield strength, we don't need any quotes because there's that. Now, I forgot to put these single quotes right here because this is another field. Okay, that's great. So home, copy, paste. And let's go for a new designation. We got so high strength, low alloy, grade 572, 572, grade 40. And the yield strength is, believe it or not, 40,000 PSI. And its elastic modulus is also 28 times 10 to the 6th PSIs. Go back here, and I forgot to change this to material 2. And let's just see if I can do this instead. Well, that was easier. Okay, so got 3 materials, 2 loading situations, 2 shapes. You are supposed to have 3 loading situations, 3 shapes, and here we are. Okay, so believe it or not, that's half the hard part. The other half of the hard part is making proper loops. Okay, so now we're going to count how many of these things we have. So we're going to do a thing called numel. So loading count. So I'm going to count the number of loads we have. equals numel and loading. So every time it sees a structure called loading that starts with loading, it adds 1. All right. And then we're going to do the same thing with shape. And we're going to do the same thing with material. All right. So I'm actually going to run this program now. Now remember, you're supposed to be commenting every step of the way. I'm showing you what to type, how to program it. You can comment it. All right. So let's hit run here. So it's going to close all, clear all, and then just set these things up. It should have pretty much nothing down here in the command window. Okay, good. But what do we have over here? Ooh, we've got a structure here and a structure here, and the loading count is 2, the material count is 3, and the shape count is 2. That makes sense. We have 2 loads, 2 shapes, and 3 materials. Excellent. So it's all working out nicely. Material, let's just see what that's. Oh, okay. So I got yield strength, elastic modulus. There we go. So now it's all getting nicely organized. And if I need another material to throw in there, boom, I just put another one in there with designation 4, and it'll just be able to move everything through without missing a beat practically. So let's get rid of that. And so I've set those up pretty well. All right, so now we are going to set up the calculation loops. Why I'm capitalizing here, I'm not sure compared to up here, but there we go. So now back to you doing the commenting. So we're going to do a for loop, okay? But let's start with I'm going to do what I call a beam calc index. Okay, so calculation index. Now some places this will count for you, but I want to keep track of this particular one for now. So I'm going to initialize this at 1 and be done with it. Okay, next I'm going to do the load index. So I'm going to initialize this value. Is it necessary every time? No, but I think it's good practice. Others might disagree. So we're going to do the load index equals 1. So we're going to initialize that as part of our load index. So so right here, you should start saying, okay, we're going to start working on the loads here. This is a big global thing. This is specifically for the loads. So and so you should talk about in your comment here what you're doing down below here in the big picture. All right. So we're going to start using for loops. Now, I really like you guys are so spoiled with the from compared to what we had, but for, okay, by the way, this is how you, if you want to not retype a whole stupid variable, hit the oh, that's right, you have to type 2 letters. Okay, oh, I guess it's not liking this, huh? Oh, I think that's because I haven't actually done. Let's see if this if it wants to run the whole thing. Okay, great. So load index shows up over here. So if I uncomment that out for load, oh, it's not really, it's supposed to be filling that in for me. Oh well. equals 1, 2. Now notice I'm using colon here, not semicolon, full on colon, to loading count. Okay, and I created loading count up here. So I know now how many load types I have. So I'm just making sure I'm going from 1 to that maximum number. Now I'm going to do another for loop. So I'm going to actually create something called shape index. Maybe I have to create it, maybe I don't, but equals 1. So I'm initializing that. So I'm commenting that out. So then I do another for loop for, I don't know why it's not letting me do the tab thing there, but shape index equals 1, 2. Oops, there we go. 1, 2. Now I find it just a good idea to copy and paste so you don't misspell things. So go up there if you possibly can. Shape count. Supposedly with the the tab, it's supposed to let you do some of those things, but oh, by the way, for that you don't, because you're not creating something yet, you don't need a semicolon there. So we're doing the for loop in here. So this is a nested for loop. So there's going to be for each one of these things, we're going to do what's below here. Oh, we're doing that again. So it's if you've never programmed before, this is a nested for loop. So a regular for loop, just for 1 to X, add 1 more or something like that, and then you just keep going that until it gets to that number X. Well, now we're going to do 3 times 3 times 3 within it. So I'm sorry if it's a little complicated for those who've never done this kind of programming before, but you know, hopefully as you type through it, you'll see how it works. So, all right, so now for shape index this, so now we're going to do the material index. Material index equals 1, and that's initializing material index. All right. Now for material index equals 1, 2, material count. So here's our 3 loops here. All right, I'm going to mention that this is for simply supported. So this is just for the simply supported. Your comment should be much more complicated, but or much more in-depth, detailed here. But I just wanted to explain it. We're just doing the simply supported one here. All right, and that means a beam with 2 supports, 1 on each end, and a load in the middle. That's all. I was doing cantilever, I think, or was I doing? Anyway, we were doing one or the other. But let's see if I can find that. Okay, so we've got. Okay, so over here, we've got simple beam. Here it is, simple beam, concentrated load at center. So that's what we're working on right now. And then there's the cantilever beam with the load at the end. That's this one here. So that's one that you can use as well. That one's relatively simple, but use 3. Okay. That wasn't very helpful. All right. All right, so now I've got 3 for loops going on here. What am I going to do about that? Okay, for that, now we are going to create beam output. This is where things are a little bit more complicated, but this is the meat of it all. Okay, this is where we're actually happening. Okay, we're going to create a new structure called beam output. And this is where up here where I said beam calc index, this is where it kicks in. Beam calc index. So this is going to be the first beam output. And we are going to call it, so the name part, so you put dot name, is going to be simply supported central load. Okay, so simply supported central load. Nope, didn't want that. I want that. Okay, great. So I'm creating this new structure, and to simply create a new variable field, we put dot name. Okay, and so it's going to be beam output beam calc index. So it's going to be 1. Beam output 1 is going to be the simply supported central load. So that's going to be the whole big thing. All the information for that simply supported central load, we're going to put this in here. Okay, and so we're going to create all the rest of the input for that beam output. So I'm going to want to kind of copy this, right? And again, you are to be going every step of the way. And I'm going to call this, oops, come on, beam, where'd it go? Beam length. And it's going to be I'm going to point at the loading situation, whatever loading thing we are on here, and that's load index. So if we're on the first load situation, this is going to point at load number 1, load index number 1. So then we call, and so we're calling length underscore feet. So this is saying, okay, I'm making this new structure called beam output, and I'm going to create a new thing called within that beam output, and it's going to be beam length. Oh, I can't even spell properly. There we go. So that's important. Beam length, and it's going to equal the loading that we're working with. Here we go. Load index. Okay. Here's a load index. So right now we're on the first load index, and that points all the way back to loading 1. So this is referring to loading 1 length foot. So now the beam output for beam length for the number 1 is going to be equal to the loading 1 length foot, which is loading 1 length foot is 10. Okay. So we are going to continue that kind of thing here. And just put the, because we're creating a new thing, I'm going to put a semicolon at the end. Okay. And beam output, beam calc index, beam length. No, we want that load magnitude. That's it. Load magnitude equals loading load index and whatever the load magnitude is going to be. Load pounds. So we're calling this one here load pounds, and just going to put there you go. And then we're going to call and create a new one for this, and it's going to be shape. And it's going to be, instead of loading, it's going to be shape, as you can well imagine. Shape index, not load index anymore, but shape index name. And now we're going to call for the calc index dot material. So we're going to define what the material is for the first one, or whichever one it is going to be material. And it's going to call the material index here. And it better not be length feet. All right, and it's just the name. But that's right, we use something different. We use designation over here. So yeah, we'd run into a problem there if we didn't use the shape designation thing. Okay, so there's our beam output starting. That kind of describes our overall beam thing. We have a beam length, a load magnitude, a shape, and a material, as well as a name for it, simply supported central load. Okay, so these 5 things give it a basic overall description. Now we get to do the calculations. So again, this is going to be another section here for you to comment. All right, so we're going to first calculate the shear force and bending moment for each one, and that is again given in the formulas on that page there. Where'd that page go? Okay, so we're going to do the Vmax here and the Mmax. Hopefully you can see that Vmax and Mmax. If you need more references, let me know, but it shouldn't be too bad to find. And the Vmax is the shearing force. So we're going to say, and the Mmax is the bending moment. So beam output again. Yeah, let me see if I can just do this. There we go. Beam calc index equals dot Mmax equals, well, we're going to do it. We're going to put units in there. Inch pounds. So notice how I specifically make sure that my units are consistent. Instead of inches per pound, which might require a slash. If I did that, I'd use an underscore. No underscore means they're multiplied. Okay, equals beam output. Okay, so we're going to use all of these things here to calculate this thing. So this is where it gets a little complicated. Copy, paste, beam calc index. Okay, which one do I want? I want the load magnitude. By the way, I'm putting a lot of spaces in there so it's easier for me to read. If you want to jam them all together, don't, because I want to read it. I mean, that's what I'm here for, right? So dot load mag times, and it's the beam output again. Beam output, beam calc index. I should really do more of this copying and pasting. Beam calc index dot beam length times 12. The reason why times 12, inches, feet to inches. So we're trying to get everything into inches, but I gave it in feet. So watch out for that. And then divided by 4, because that's part of the formula. So the formula is the load times the length, and you divide that times 4. That's the maximum bending moment. Okay. That's over here somewhere. That's where to go. Here it is. M max P times L over 4, right there. P times L over 4. So the load times the length, but you have to have consistent units, divide by 4, because we're eventually going to get everything into pounds per square inch, and we'll have to get rid of all those lengths of feet. Okay, so that was that. So let's see if we can make another similar thing. All right, so we're going to do Vmax and that's going to be in just pounds. And we're going to take the magnitude times the output and simply divide it by 2. Okay, and again, this is specifically for, and I get rid of the extra parentheses. This is specifically for the simply supported one with the middle, so you'll have to do 2 ways. Okay. Beam output. So that's calculating the shear force and bending moment right there. Okay. Next section, of course, you're going to have to comment these all on your own. We're going to calculate the stresses. So going to create a new one. Oof. Okay. Beam calc index dot. We are going to make the flexural stress. And that's going to be in PSI equals beam output, beam calc index again. Put this in parentheses because we're going to need that. And now we're going to use this beam output that we just created, M max in inch pounds, because we're going to use that M dot M max inch pounds, and we're going to divide it by the S, so M over S. So got shape index dot SX underscore inches cubed. Okay, so what did I just type there? Okay, so we took our beam output, which was our M max that we just calculated up here. The formula is M over S. It's pretty simple, M over S, but we had to call the correct S over here. So we went to shape index dot SX inches cubed. So so whichever shape we're doing at this point in time, that's why we put shape index here, not just 1, 2, or 3. But if we go up to shape over here, that's what it is, shape 1, and we call on SX right here, SX inches cubed, and it's going to call this value when we do that. So I'm going to get rid of the rest of that stuff. Okay. So it's going to call that shape value, shape index, which shape 1, and that's the value we want. That's the value of that field. That's what we're trying to get. All right, so then do something similar here. And paste. Okay, beam output, blah, blah, blah. So we're defining the beam output called shear stress, right? Shear stress, PSI, beam output, B calc index of, we want to use Vmax in inch, not inch pounds, just pounds. And then it's supposed to be shear stress for a beam like this is approximately V over D, the depth, times the thickness of the web. So we've got to calculate those out. And those are shape properties. So let's go to shape index. And instead of SX, we need to use depth inches times, again, shape index. I'm going to copy this. Shape index, and I want TW. Not quite sure what I used here. Web thickness, that's what I want. Web, THIN. Okay. So let's see if I've got the right number of parentheses here. Yeah, that looks better. Okay, yep, got those parentheses, good. Okay, so we took whatever shape index we're on, whatever shape we're on, the first shape, say, we just called its depth in inches multiplied by its web thickness in inches. Okay, good with that. All right, we are getting down there. Okay, deflection and ratio. So copy, paste. So now we are going to use those, perhaps, to create the deflection in inches. And now, okay, so we used the loading situation, the shape, the material. Now we're going to go back and do, we used again the load, we used these things up here to create our Mmax and our Vmax, but then we had to go back, start using our shape again. And we still have yet to do using the materials. So here we go. All right, so we're going to calculate the deflection. The deflection is a little bit more, this is the most complicated one of all of them. It's still not terribly bad. I mean, if you can do algebra, it's not bad. But here we go. So we're going to go to our formula again. Oh, sorry, we don't. Yeah, here we go. Delta X is what you're going to be looking for. So we've got concentrated load at center. It's going to be PL cubed over 48 EI. So right here is where that's going to be. So PL cubed. So P is our load. So that's going to be this bad boy up here. Okay, so loading. Oh, we're just going to go with loading on this one, I guess. Here we go. Loading index. Nope. Loading index. This one. This one. Load in pounds. Open parentheses. Loading and load it in pounds. And then we're going to multiply that P L cubed. So we're going to want to open up more parentheses. And that's going to be our length right here. Length and feet. Copy. Paste. But we have to multiply it by 12 first. And then we can raise it to the third power. And then we can put it back in the parentheses. So PL cubed, then we're going to divide it by 48 times E times I. So what's E? E is our material thing. So we've got to figure out which material we are going to be using. So material index, we're just going to copy this here. And instead of name, we're going to call elastic modulus. How did we call that? Here it is, elastic modulus PSI. Elastic modulus PSI, close parentheses. Oops, we forgot about I. So we have to multiply that times our shape index. So where's the shape index instead of desig? It's going to be shape index I, which is I in the X direction. I about the X direction. So it's IX inches to the fourth. Okay, whew. Yeah, that one was tough. That was the longest one. Okay, so we got the deflection, Again, that's the most complicated, so that's good. And next we're going to do the yield ratio. And that what that is just a fraction of how close we are to the yield strength. So that can be a variety of things, but it's kind of like a quick factor of safety, if you will. So, but it's not an actual factor of safety. We'll talk, that's a different story, but it's a rule, just a basic, how close are we getting to where we don't want to be? So we'll go call it yield ratio. All right. And find beam output. Oh, we're going to use beam output here, which is our flexural stress. Right? In PSI. And we're going to divide that by the material yield strength. So wherever that went to, okay, so it's going to be this yield strength PSI thing. So if I can copy that. Okay, so yield strength, where'd you go? Here. Okay, so we divided the 1 by the yield strength, by the stress that we have, divided by the yield strength of the material. So once we get to the material's point, then we know that it's going to start breaking, and that's bad. So we don't want, we want this well under 1.00 if possible. All right, hopefully that's helpful. All right, so that was the heavy lifting. That was all the heavy lifting. So now we're going to display it. Display beam output. And it's going to be the beam calc index. Okay, so beam output, beam calc index. That's about it. And then we are going to iterate that. So where we started way down here, beam calc index equals 1. We're going to do beam calc index equals 1 plus. So we're going to add that in. Equals beam calc index plus 1. Now, what I'm really showing you here is the old school way of doing it. The Matlab actually will iterate anything in a for loop automatically. You don't have to tell it to. So what we're going to do here is now we are going to end the loop. So we're going to end, and notice how the for just highlighted. Watch this. Aha. Notice that this 4 up here has a red underline. That's because it's missing an end. So I hit end here and I hit enter. And then I'm going to hit end here, enter. And then I'm going to hit end. I'm going to type end here and enter. And it automatically knows these things. However, if you have a long program and this is long enough that we can't really see the top here, you should, of course, comment every single step of the way. What's this for? What's that for? What's that one? Literally, what's that for? Which for what are you ending right there? Okay. So now what you'll want to do is do all of this again. Basically, you're getting probably do a lot of copy and paste, for simply supported for another one of things that's not simply supported. Maybe a cantilever, maybe one of the other ones, but do your best to keep it simple. But you're going to want to do this again for another one of those. But what you're going to have to do is you're going to have to change the calculations in here, because those formulas are going to be different. Oops, forgot to put that there. All right, so that is your assignment. So you're going to have 3 of these loops. So this is all the heavy lifting, but you'll just have to copy this and then go back and change some of these formulas for that particular load. So you're going to need to change the M max, the V max, the flexural stress, the shear stress, the deflection, and then calculate the yield ratio. That formula is not going to change, but all of these 5 are going to change depending on what type of loading situation you have, simply supported or something else. Okay, so let's run this and see if I did anything bad. Yep, I did something bad. So what, column 155, not bad. White. Oh, sorry, line 52. Use parentheses. Oh, probably missed a parentheses somewhere here. Oh yeah, it doesn't like a whole lot of stuff here. Isn't that great? Line 55 might be missing stuff. So let's see if line 52. Okay, it looks like says, okay, so we've got beam output times that. I think I need I'd like to put parentheses in here anyway. Yeah, that must have been it. So take that, divide by that. Okay, so what other bad things do I do now? Okay, so fix that, 55. It's probably a similar kind of thing. Yep. I think I didn't put it in the top there. And then this one, I think I copied and pasted. That's the problem with copying and pasting. You also copy and paste mistakes. Okay, 58. Something similar. All right. 62. Does not like what I'm doing here. Oh, duh. I should have seen that one too. Haha. Success after I just put in all the parentheses I used. Okay, so you see here that I came out with a bunch of great information. So now the display is simply supported, beam length 10, load mag this. Okay, so these are the basics. So here's my output. This is how much bending moment I have. This is how much shear force I have. Here's how much flexural stress. Here's how much shear stress, the deflection in inches, and the ratio of yield. So I'm way under the yield strength, which means it's probably way over engineered, but that's that's okay. And so I can see for each one of these cases, exactly what's going on, which is pretty cool and very helpful. And it organizes it differently than, say, an Excel spreadsheet would. And from here, we can do a lot more with it, but this is all we can afford to work on this semester. Now, if I wanted to go over here to the beam output, I can also look at it in a tabular formula. So here's the name, and so therefore that's basic description. It's simply supported. If I had another set, I'd come down here and have a whole bunch more. What's the beam length here? The magnitude of the load, and so on. So I did 2 and 20 here, and 10 and 10,000. It'd be very easy to add another set in there, and I get the flexural stress and PS and our yield ratio. We can see that our yield ratio is if you will, the closest. All of these are way under, but with these particular setups here. Okay, so I hope that this helped, and good luck in getting this taken care of, and I hope you learn a few things too. Send me any questions if you have any, and I'll do what I can.